Chapter 6, Part 2 review. So this first part, we're evaluating the expression. That means I'm not using a calculator. So I'm trying to figure out what angle produces, what cosine of what angle produces root 3 over 2. So you can do the left-hand method. You could do a triangle. Doesn't matter. All right, we're looking at the unit circle. Cosine root 3 over 2. Now root 3 over 2 is bigger than 1/2. So cosine is your x, while sine is your y, right? So this distance, the red, is longer than the blue, right? So that means root 3 over 2 would be the bottom, which is our x, which is cosine. So this angle that produces this is a pi sixth, right? Or you can do the left-hand method. 1, 2, 3, 4, 5, 0, pi sixth, pi halves, no, pi fourths, pi thirds, and then pi halves. Okay. And so this 6, if I put that finger down, it's always square root of how many fingers are up divided by 2. And so cosine is always to the left. So I have 3 fingers up. So it's root 3 over 2. So that it would be, our answer to this is pi sixth. But if you're looking at the unit circle, this is a positive root 3 over 2. So where's cosine positive? Well, it's in the first quadrant and it's in the fourth quadrant. So that would also mean pi sixth is an answer. So is 11 pi sixth, because that'd be the fourth quadrant. So those two answers. All right. This one, whenever I have the inverse. Whenever I'm taking the inverse of the function at some value, it's always going to equal that x, right? It's always going to equal what I'm taking the function of. Because basically it's saying I am plugging some value into my function, and then I'm plugging that answer into the inverse. Well, that's always going to give me back to my original, right? So this is saying that here I'm taking cotangent of some angle, which is going to give me an answer, but then I'm taking that answer and figuring out what is the angle that produced that answer. Well, that's for y, whatever this Greek symbol is. I don't know, but there's your answer. All right, this next one, 3/4. 3/4 we don't have, so we can't do the left-hand method, nor do we need to use a calculator either. But if I'm looking at cotangent of some angle equals 3 over 4. That's what that's saying, right? So cotangent is x over y. So I could use Pythagorean theorem to find out what my r is. So that would be 3 squared is 9, 4 squared is 16, 16 plus 9 is 25, square root of 25 is 5. So my x is 3, my y is 4, and my r is 5. Now I can go ahead and find, so that gave me, that's for the angle, right? Or you could draw a triangle. Here's my angle. Cotangent would be adjacent over opposite. And so I could use Pythagorean theorem, solve for this one. Now I'm looking for secant of this same angle, and secant is adjacent over hypotenuse, so 3/5. Or secant of an angle equals x over r. So here's my x3, here's my r5, 3/5. Okay, so there's your answer for that one. This one, cosine of pi halves, I can actually do that on my left hand. However many fingers that is, 1, 2, 3, 4, 5, hey, that's 5 fingers, and 2 pi, so I put this one down. So cosine's to the left, so that's 0. So square is 0 over 2, so that's just 0. Now, what angle gives me a sine of 0? Well, that is at 0 and at pi, right, on the unit circle. Right here, this point, that'd be 0, 1. So my y value, 1, 0, geez. So my y value is 0. Here is negative 1, 0. Again, 0. So I have those two answers. All right, let's take a look at this one. We're looking at a bacteria. So we're looking at either, you can do y equals CE KT or A per. It doesn't really matter. It's the same thing. Right, we have some type of rate of increase, or rate constant maybe, and some time t raising it to e, and then we have some principal or some starting amount, same thing. Okay, so here they say what the starting amount is, 200. So y equals 200 EKT. So we still have 1, 2, 3 more variables, so we need to fill in 2 of those. Okay, and then it says, okay, after a half hour, so that would be time equals 0.5. our population, which is y, our amount in the count at the end, is 360. So I can plug in 360, because first I have to find out what my k is, 0.5. So I plug that in. This equals here, divide by 200. So we get whatever that is. I don't know. I just leave it. I can just leave it like this. Right? That'd be multiplying there. Then I take the ln of both sides. So I get ln of this. If I want to add 0, I could add a 0, or I could leave the 0 off. That's fine. Ln of this side is just k times 0.5. Right? So then I just divide by 0.5 on both sides. So there's my k. And I can simplify that, and I think I get this for my k, 1.18. Or I could leave this in. If I leave this in, I'm being more accurate, just like that. And then here's my t. So there's my a. Now I want to figure out after 4 hours. Well, that's when I just plug in 200, push e, raise it to 1.18, and plug in 4. And I get 22,434. So there's my B. Now my rate of growth is how much my growth changes in 4 hours, over 4 hours, right? So it's just your slope equation, right? So it's taking in 4 hours, how much does it grow to? The 22,434 minus how much I started with, and then divide that by my time, the difference in time, which is 4. So that one I get, let me see, 55,558.5. So there's my answer to C. That's how much it's growing each hour, right? For every hour, it's growing that much. So there's my answer for that. And then D is how long will it take to get to 10,000? Well, that's when I put 10,000 in for my Y. My C is still 200, or my P, whatever. E, my K, or my rate is still that whatever. I rounded it. What's this number right here? So if you didn't round it, you're going to have a little bit different answers than I would. If you just left that in as ln of 36 over 20 over 20, then take the ln of that and then divide by 0.5. Okay, well, anyways, you plug this in. This is 10,000. There we go. So I divide by 200, and then I would take the ln of that. So I'll cross out those two zeros. That's 50. So ln of 50 equals 1.18 t. So divide ln of 50. ln of 50 divided by 1.18 equals 3.31. So 3.32 hours. How many hours it would take, approximately. Okay, so here's this one. Same thing. It's asking for a half-life. So again, you really don't actually need to put in a C or a Y, because you know that they're half of each other, right? So if this is 2C, this would be just C, right? But you could put in numbers if you want to. And because I'm decreasing, my K is going to be negative. All right, so I could put in numbers like 100 for my C, because that's what this scenario gives, right? 100. So that means when you get a half-life, you would have 50, right? So it really doesn't matter, because when you divide these, you're going to get a half here. You're going to get a half, and you're going to take the ln of both sides. So you're going to take ln of a half equals kt, and you're going to divide by your t, which again, it gives us our t. So that's how you can figure out any k for any half-life. Right, it's just ln of a half divided by how much time it takes to get to half-life, which is ours is 5.24. So you could really leave that in there. So we start with 100. So I could really leave this in there, ln of a half over our time, which is 5.24, and then times that by t. That's a more accurate reading, but I rounded it negative 1.132, I believe. And my t, e 100. Now I can go ahead and plug in 20 for my t. So I plug in 20, plug this in there, see what I get, and I get 7.136. That's how much will remain, so that's milligrams. Okay, and then I can ask the second question, how much to get to 1 gram? So I start with 100, I end with 1. My K is like I said, I rounded that point, negative 0.132. And now I'm solving for T, so I'm going to get the E by itself first. You could do decimal there if you wanted to. Take the ln of both sides, so I'm taking the ln of this. And then going to divide. This time I'll divide by my K, right? Because when I take the ln of this, that's gone. And so I'll divide by my K, 0.132, and T. So I do that and I get T equals 34.89. So about 35 years. So about 35 years. That's how long it's going to take to get to 1 gram if I have cobalt 60. All right, so let's go ahead and differentiate now. So we're going to differentiate this. We have 2 terms here, right? So we're going to have to do product rule. You might hear somebody's sirens going off in the background. You might hear in this, so I apologize if that's the case. So that'd be F times G prime, or the backwards, whatever, plus G prime, or addition, it doesn't matter. With product, it doesn't matter which one is the case, because we're adding here, but the quotient rule does matter. Okay, so take the derivative of that. That's just going to be 1, so F prime is 1. G prime would be the derivative of tan inverse of phi, and tan inverse, if you look it up, I'm looking at the hyperbolic ones right now. I don't want to look at the hyperbolic ones. I want to look at, and that's tangent. All right, and so tangent is, derivative, there it is 1 over 1 plus v squared. So the derivative of G is going to be 1 over 1 plus v squared. Okay, and if you have anything other than just v, you would be doing chain rule, right? So then I would times this by the derivative of whatever v is. If that was v squared, then it'd be 2v. Right now, I'd leave this as v squared, so that'd be v to the 4th, if that makes sense, unless I'm talking too fast. All right, so F prime 1 times G plus G prime, which is 1 over v squared, times F, which is just v. So we can simplify this, tan inverse of v plus v over 1 plus v squared, and that, I believe, is good enough. Yeah, that's good enough. But I mean, basically, I mean, you could, if you're ambitious, you could change that to what it actually equals, which I think in your books is like page, no, maybe it's just the hyperbolic ones that are explained out what they are. Yeah, so that's good. All right, here we go again, product rule. So here we're going to have product. So this is my F, this is my G. Derivative F is just 1. Derivative G is going to be chain rule. Kind of like what I was talking about the other one. So that's the derivative of the outside, which is a hyperbolic, right? So that's a hyperbolic one. And again, this is product because I have multiplication in there. So I got to look up the hyperbolic one. So hyperbolic sine. You got to see what hyperbolic sine is, the derivative of that, which is hyperbolic cosine. So hyperbolic cosine, why am I doing that? Okay, I leave the inside alone, and then I times it by the derivative of the inside, which is derivative x squared, which is just 2x. Okay, so that's the derivative of G. Now I do product rule, right? So F times the derivative of G, so 2x times x, which is just going to be 2x squared, hyperbolic cosine of x squared, and then plus the F prime, which is 1 times times just g, right? 1 times that is just that. So there we go. And I think that's as far as you need to go. Yeah, that's all good. Okay. Okay, next one. You're going to be taking the derivative of ln. And now it's ln of something. There's probably like 2 parentheses like that. So you take the derivative of ln, which is 1 over x. So that means I leave the inside the same. And then times that by the derivative of the inside. Well, the derivative of the inside is also a chain rule. It's hyperbolic cosine, which the derivative of hyperbolic cosine is hyperbolic sine. Leave the inside the same, times by the derivative of the inside, which is just 3. So this is just 3, right? So I got to times, I'll just move that 3 up front like that. So really I got to times these two. So it's 3 hyperbolic sine of 3x over hyperbolic cosine of 3x. And then you could simplify that since they're both hyperbolic sine over hyperbolic cosine in the same angle. Then you could just do hyperbolic tangent of that same angle. Either one of these. That's not a negative, that's an equal sign. So remember, anytime you take the derivative of ln of any type of function, ln of any type of function is here, then it's just going to be the derivative of that function over whatever that function is. It's kind of not prime on bottom, just like that. It's pretty easy. I don't know if I pushed record, but I guess I'll quickly do this one again. Finish it. So I have hyperbolic sine over hyperbolic cosine with the same angle, so I could really just move that to hyperbolic tangent with that same angle. And then anytime you take the derivative of ln of any type of function, it's just really the derivative of that function over that function. So it's pretty easy. All right, so let's go ahead and look at this one. So now we're taking the integrals, right? So anytime we take integrals, we're going to take it, this du part is telling us, so dx, dt, du is telling us what we're doing it in terms of. So we're actually doing it in terms of u, but this has an a in front of that. A is just a constant, any constant. So anytime I don't have other than just u, or either just x or just t, then I have to do substitution rule, right? So I'm going to let u, well, I guess I would have to let it something else. Normally we do substitution rule with u, but u is already in there. So let x equal ax, au, sorry, au. Take the derivative of that, so dx equals a du. And now substitute in my x for au. So the integral of hyperbolic sine of x du. And then so my du, I want this to be just dx. Well, dx is a over du, so I have to divide by a on both sides. So this du is equal to dx over a. So this du right here is going to switch to dx over a. So that a is just a constant, so I can bring it out front. Oh, there's an x in here, and there's an x right here. Okay, so now I'm taking the integral in terms of x with just an x. So now I'm good. So now I can take the integral of hyperbolic sine, which is hyperbolic cosine. But my x is au, right? So now I got to substitute that in. Maybe I should put this closer together. Hyperbolic cosine of au times 1 over a, and then I got to add c at the end. Okay, so there you go. These integrals are a lot harder, right? So you have to look at, because there's no list of integrals of these ones, so you have to look at the answers of the derivatives and basically go backwards. So if you look at the answers are all the derivatives, so like for instance, you have this inverse hyperbolic sine. I don't know why I put an h there, it should be a -1. Okay, or x. There's an h here and an x here. equals 1 over square root of 1 plus x squared, okay? So what you do is basically you take that list, erase this dx, and put an integral sign right here and add a dx right there. There you go. That's what it'll equal. So that's how you can come up with the integrals. So you have to fit something that has the form of the answers. So I'm looking at this and saying, okay, which one of my answers of my derivatives look kind of like this? And the only one that kind of looks like this, notice that this doesn't have a square root. So that eliminates all of them except for hyperbolic, inverse hyperbolic tangent, right? And if I look at just the regular ones, the regular hyperbolics, those are plain straight across. Those are pretty easy to go backwards. The inverse ones are looking like this, right? So that means this is probably going to be, the answer to this is going to be in some form of inverse hyperbolic sine or inverse hyperbolic tangent, okay? Because that answer, the derivative of that, there should be an x there, looks like 1 over 1 minus x squared, right? So it kind of looks like this form, right? We have something squared on bottom, but this needs to be a 1, correct? So we're going to have to manipulate. We're going to do substitution. Oh, wait, I did find some integral answers. If you look at page 458 and 459, there are some answers actually of not the hyperbolic ones, but of the regular inverse sine and inverse tangent. So this is actually going to look sort of like an inverse tangent of some sort. And actually on page 459, you have this one. What's the integral of something 1 over, which we have the 1 over, x squared plus a squared. So we actually have two things being squared, which we do have two things, and this is not 1, right? We could take that 16 and make that a 4 squared. Okay, so now we kind of fit this form. And this is actually equal to 1 over a, so whatever's being squared, that second thing being squared, which 4 is being squared, so that would be our a, tan inverse of x over a, and then add c at the end. So this is actually pretty easy. So so make sure you have all those things highlighted and read down. So here we go. So we know our a is going to be 4 and our just plain x is going to be t, right? So the integral of this from 0 to 4, we're going to have to plug in 0 to 4 here, is going to be 1 over 4 tan inverse of x, which is t, over a, which is 4. And now we're going to do it from 0 to 4. So I want to plug in 4. So this is where it gets tricky. These ones are a little bit tricky because now we're actually going to use what tan inverse actually means. I believe that's what we're going to do. Maybe not. We'll just go plug it in right now. So let's plug it in right now. So we're going to plug in 4. 4. And then minus plugging in 1, or plugging in 0. Okay, so we can simplify that, right? Oops. Okay, so 4 over 4 is just 1, correct? So what is tan of 1? What gets you a 1? What angle gets you a 1, right? That would be 45, right, or pi fourths. And 0, what gets you a 0? Well, that's going to be a 0, correct? 0 degrees, 0 times 1/4. Right, because on the left-hand method, 3, 4, 5. On the left-hand method, tangent is right, square root of the right, over square root of the left. So when I plug in 0, what's going to get me a 0? Well, it's going to be 0 on top, right, to the right. So I got to plug this one down, so that's going to be 0. So I get just pi 16ths. So my answer should just be pi 16ths. Perfect. So your answer is pi 16ths. So that actually didn't turn out to be pretty bad because there was actually some integrals of the inverses, right? There's some integrals of inverses, tan inverse of x dx. So we'll get those down. All right, this one, what does this one look like? I guess look for those integrals that are actually given to you, right? So this one looks like 1 minus x squared on bottom it kind of looks like sine inverse, right? The integral of sine inverse, except for we have this 4 on top. Well, it's a constant, right? That 4 is a constant, so really we can just put that on the outside. And really this one right here is really the same as root 2 over 2. If you rationalize it, which is better because we know that one better, right? That gives us, dealing with tangent, that gives us, or dealing with, we're going to deal with sine, but that gives us pi fourths, right? Dealing with sine. Okay, so anyways, 1 over square root of 1 minus x squared. So this looks like a tangent, or sorry, not a tangent, a sine inverse. So that looks like sine inverse. 1 over square root of 1 minus x squared dx equals sine inverse of x. Right? So there, this is just be sine inverse times 4 of x times 4. And then we're going from 1/2 to root 2 over 2, which is the same as 1 over root 2. All right, so which means I have to plug those in, which kind of stinks. So 4 times sine inverse of root 2 over 2, which we know root 2 over 2, what angle of sine gives us root 2 over 2. Like I said, that was pi fourths. Times by this 4 is just going to be pi. Getting sloppy. I'm getting sloppy. Minus 4 times sine inverse of 1/2. So what gives us 1/2? Well, that's pi sixth. Times by 4 is 4 pi 6. We're going to subtract that. 6. So this is 6 pi 6. So that'd be 2 pi 6, which is pi thirds. Let's go ahead and check that. Perfect. Great. Pi thirds is your answer. Yeah, these parts when they add in the A and the B, that kind of stink, but it's not too bad. So it's really nice when you just add the at C, right? That's a little bit easier. All right, so this one is definitely harder, but I actually think I did this in a video recently. So it must be from your homework. Probably an even problem or something like that, since I give you mostly odds. Okay, so here, nothing looks like that, right? The only thing it kind of looks like that is back to your original, your hyperbolics, right? But nothing with a fraction like that. So we know it's going to be a hyperbolic, a straight hyperbolic, no inverses because there's no square root division with a square root in there, or a division with an x squared on bottom, 1 plus x squared or 1 minus x squared or anything like that. So we know it's going to be hyperbolic, but there's no direct substitution here. So what we're going to have to do is we're going to have to do substitution with u. So we're going to let u equal something that we know the derivative of. Okay, so a lot of times when we take the integral, we know the integral of 1 over x. Okay, that's ln of x. I think there was a problem in the review where I was trying to take the integral of that, ln of x, which is integral by parts. So that we don't know how to do, and I think I just told some people what it actually is. But I know the integral of 1 over x, that's ln of x. Okay, so if I can get this to the integral of 1 over u du, then I know that's the ln of u, right? So I want this to be 1 over something. So that means I need to let u equal the bottom. That's my best chance. Now the derivative of this, the derivative of 2 is just 0, right? The derivative of hyperbolic tangent, if you know it, it's going to be what I need, right? Because if I substitute in my u right now, before I even take the derivative of my u, I have 1 over u times secant, right? Because I'll do it the long way real quick. I have secant, hyperbolic secant squared of x over u dx, right? Which is the same thing as 1 over u times hyperbolic secant squared x dx, right? So I need my du to equal that, right? So I know this is probably going to be the derivative if I look at my derivatives of hyperbolics, right? So the hyperbolic of tangent is, the derivative of hyperbolic tangent of x is hyperbolic secant squared x. And I have dx right here. So that's a direct, perfect. du is that. So that right there is du. So now I can take the integral of that, which I do know is ln of u. I can go ahead and substitute in my u, which I know is 2 plus hyperbolic tangent of x. Now I'm going to take the ln of that, right? Let me see if that's as far as we need to go. Yeah, that's as far as we need to go. Let's just add a c to it. That's nice when you just have to add a c, right? All right. All right, let's look at the last one. Hopefully, all right. L'Hopital's rule. So L'Hopital's rule, we deal with indiscriminate or indeterminates before, you know, like we got like 0 over 0 or 0 over infinity and stuff like that. Well, L'Hopital's rule, before we weren't able to solve those. Well, L'Hopital's rule allows us to solve those. So anytime we get an indeterminate, we can go ahead and just take the derivative of the top and the derivative of the volume and plug in our 1. So anytime we plug in our 1 and we get 0 over 0, right? Then we can just take the derivative of the top and the derivative of the bottom and then re-plug in our x into our derivatives. And again, if we get 0 over 0 or infinity over infinity, then we can go ahead and take the second derivative of each of them and then plug in our x again and see if we get some actual numbers here. So that's what L'Hopital's rule suggests, is basically just taking the derivatives of these things. All right, so we're going to go ahead and take the derivative. Well, we're going to plug in 1 first, okay? So 1 minus 1 over ln of plus ln of 1. And then all over 1 plus cosine of pi x, right? So I'm going to plug in my 1 for x. So that's cosine of pi. Cosine of pi is just 0, right? 0 plus 1. Or actually, it's negative 1, sorry. Is negative 1, which gets me 0. That's the whole point. I want to get 0 over 0. Now the top, I get 1 minus 1 is 0, of course. And then I'm adding L of 1. Ln of 1 is, what do I log base e of what would get me 1? Well, that'd be 0. So 0 plus 0 is 0. So I get 0 over 0. So that means now I can use L'Hopital's rule. L'Hopital's rules means I can take the derivative of the top, which is taking the derivative of this over the derivative of the bottom. And then I can go ahead and plug in my x. I can plug in my 1 again into these two derivatives and see if I get 0 over 0. I'm looking to get a number over a number. Or even if I get 2 over 0, perfect, that's okay, it's undefined. Okay, I just can't have 0 over 0, infinity over infinity, that kind of thing. Those indeterminates. And then I'm taking the derivative of this. Okay, so the derivative of the top is pretty easy. Derivative of 1 is just 0. Derivative of x is negative x. Derivative of negative x is negative 1. Derivative of ln of x is 1 over x, right? And so then the derivative of the bottom, derivative of 1 is just 0. Derivative of cosine of pi x. Derivative of cosine of pi x equals chain rule, right? So leave the inside the same, or take the derivative of the outside, leave the inside the same. And then times that by the derivative inside, which is just pi. Okay, so negative pi sine pi x. Now we can go ahead and take the limit of that as x goes to 1, meaning I can plug in 1. So I'm going to plug in 1 here, plug in 1, I get 1. 1 minus 1 is 0. That's fine so far. I just can't have 0 on bottom, right? So when I plug this in here, I get 0. Well, sine of 0 is 1. And times 1 times negative pi is just negative pi. That's not negative pi. 0 times pi is just pi. Oh, plug 1 in. I gotta plug 1 in. That's just pi. Sine of pi is actually 0. 0 times negative pi is 0. So I got 0 over 0 again, right? So that means I can do L'Hopital's rule again. So I'm going to plug in, I'm going to take the derivative of the top. So I'm going to take the derivative of minus 1, which is 0, and 1 over x. And so then I'll take the derivative of the bottom. So negative pi times cosine of pi x. And then I'll take the limit of that as x goes to 1. All right, so the derivative top is not too bad. This can be rewritten as x to the negative 1. So when I take the derivative of that, I get negative 1 over x to the negative 2. So that's just 1 over negative 1 over x squared. So that's my top. The derivative of the bottom is, really I can just take the negative pi out front. That's fine. Yeah, so I can just bring this out front because it's just a constant, right? It's just a number. And then so I'm taking the derivative of this, which again is chain rule. Derivative of, oh, why did I write cosine? Sorry, that should be sine, right? So derivative of sine is cosine. So cosine, leave the inside the same, and then take the derivative of that, which is just pi. So we get pi out here, but then you have another pi, right? That negative pi from that one. So you get this like that, and then we can plug in our x's, take the limit as x goes to 1. So I'm plugging in 1. This is just going to give me negative 1 on top. And then on bottom, I get cosine of pi. Cosine of pi is negative 1. So I get a negative 1 here when I plug in that. So negative 1 pi times pi is just pi squared. So I get a negative pi squared. These two times each other is just positive pi squared. So now I actually have an answer of negative 1 over pi squared. So that's how you use L'Hopital's rule. All right, and that's the end of this chapter 7. Sorry, not chapter 7, chapter 6. Jeez, silly.